This is the lesson on mathematical formula calculations. The first one that we're doing is percent composition. By the way, we've done most of all of these last year, so you shouldn't have too much difficulty, or a few wrinkles, of course. What's percent composition of C3H5NO? Well, that's all the information they give you, so you do it from the atomic formula using the periodic table. Carbon, 3 times 12 is 36. Hydrogen, 5 times 1 is 5. Nitrogen, 1 times 14 is 14. Oxygen, 1 times 16, 16. You add those up and you get 71 for the denominator. Now you do the math and you end up with 50.7% carbon, 7% hydrogen, 19.7% nitrogen, 22.5% oxygen. If you add those up, you get 99.9. There's going to be some rounding errors in here. So if you go to the nearest tenths and you're between 99.9 and 100.1, you should be fine. Next thing is calculating the empirical formula. There is an algorithm. Follow on this. If you're given, step 1, if you're given the percent, change to grams. Then, if you have grams, you change grams to moles. Then you divide by the smallest number of moles. If it's a whole-ish number, it's close to being a whole number, within a tenth or so, round it, and those are your subscripts. If, however, you got a substantial decimal, then you got to multiply all of them by a multiplier to get rid of it. So if you have something that ends up with a 0.5, if you multiply every ratio by 2, then that'll eliminate that 0.5 and you'll get whole numbers. If you're close to 0.33 or 0.67, this is 1/3 and or 2/3, so you'll multiply everything by 3 and round, get that. Now if it's 0.32, 0.31, 0.35, go ahead and multiply by 3 and round off. If you are at 0.25-ish or 0.75-ish, then you multiply by 4. There are other special cases where you would multiply by something like this. Generally, if it's only going to be a 2 or a 3 on most exams or things like that. So, for the example on this, if you have a compound that is 40% carbon, 6.67% hydrogen, 53.3% oxygen. Well, the first step you do is you have to move those to grams, which is a very easy thing. You just call it 40 grams, 6.67 grams, 53.3 grams. And then you divide by the molar mass, change to moles. So 1/12, 1/1, 1/16. So you multiply those out. This turns out to be 3.33333. this is 6.67, and this is 3.331, blah, 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 round it off. Smallest number, 3.33. The top one is 1, the bottom one is 1, and this one is darn tootin' close to 2. So CH2O would be the formula for that. There is another type of problem, this is new, where if you have a hydrocarbon and you burn it, if you burn a hydrocarbon, you'll end up with carbon dioxide and water. And when you do this, you have carbon dioxide absorbers and water absorbers, and you can weigh the mass of the thing before and after, so you can find out how much carbon dioxide and how much water was produced from a set amount of sample. And if they have to be consistent with the whole content, then that's it. If there's something else that's remaining, then you got some other element like nitrogen or something else in there that will not be absorbed. We're going to do the simple problem, for example, here, and then class will probably hit it, the more complicated one. Suppose you burn a sample of hydrocarbon, and you end up with 33 grams of carbon dioxide and 13.5 grams of water. Well, the carbon dioxide comes, hydrocarbon is made up of carbon and hydrogen only. Well, if you burn this, you're going to react oxygen, that's what burning means, with the carbon, you're going to form carbon dioxide, and the hydrogen is going to react with oxygen to form the water. So what you got to do is find out what fraction or part of this carbon dioxide is carbon. Well, carbon is 12 grams from the periodic table, and CO2 is 44 grams. That means 12 out of every 44 grams of this compound is carbon. So if you multiply by that ratio, you'll get 9 grams of carbon. You're eliminating the oxygen, in other words. Doing the same process here, water has 2 grams of hydrogen in it, and the entire compound is 18 grams. So if you do that, multiply it out as 1.5 grams of hydrogen. Now we can do like we did up with the empirical formulas. 1 over 12, 1 over 1, and that will give you moles, which is 0.75 moles of carbon and 1.5 moles of hydrogen. Divide by the smaller, and you get a 1-to-2 ratio. So the compound, initially, empirical formula, CH2. If you had something else, there would be another step in here that you'd have to do. Originally, the compound would have had to consist of 10.5 grams. If this number here, when you added them up, was less than 10.5, say 9.5, then you have 1 gram of some other chemical, say nitrogen, if that's what you're given. Then you'd have 1 gram of nitrogen, and then you'd have to do the whole process with that. So when you get to this step right here, add it up and see if this is how many grams of the sample you had originally. If it is, you continue on. If it isn't, you subtract the this mass here from the sample, say it was 11.5, and then you go on. Okay, so that's new for this course. The next thing is molecular formula, and the last thing, you have the empirical formula, or you calculate the empirical formula, and you know the mass of the entire thing. So you have your given molecular mass or molar mass of the compound, which we can find out, and we are going to find out these things later in the year, divided by the mass of the empirical formula. That gives you the multiplier. If this is 3, that means the real thing is 3 times heavier than what it should be. And I can't spell multiplier. Okay? So, for example, you have a compound with an empirical formula of NO2 and a molar mass of 92.01 grams per mole. So you find the molar mass of NO2, 14 plus 2 times 16 is 32, is 46. So you divide the empirical mass, 46, into the molar mass, 92, and you get something darn close to 2. So it's really 2 times bigger. So it's not N1O2, N2O4. That ends this lesson on calculating empirical formulas, or calculating formulas.